Good afternoon, guys. Welcome back into my channel. So in this lecture and lab, we're going to understand and configure NTP. So NTP is an internet protocol that's used to synchronize the clock on computer network to within a few milliseconds of universal coordinated time. It enables device to request and receive UTP from a server that in runs receive precise time from an atomic clock. So you may ask, what is NTP? Well, a man with one watch clock, with one watch knows what NTP is. A man with two watches is never sure. So Siegel law pokes fun at the person who makes no effort to check the right while highlighting the complexity of receiving information from one or more sources. When it's come to synchronizing your operation, network time protocol solves both problems, providing user with the certainty of accurate time across a whole network of devices. Like any network protocol, NTP is a set of rules or convention that dictates how devices on a network should transmit, receive, and understand data. Think about it as a shared language, allowing device to communicate, in this instance, about time. NTP allows network devices such as clock, phone, and computers to request and receive time from a server that receives precise time from a definitive time source, like an atomic clock. Now, NTP was developed in 1980s and is now on version 4 since its release. It's been used to synchronize the critical system of businesses, organizations, and government all over the world. Why is time synchronization is important? Well, precise time is vital to everyday life. As life becomes digitized and automated, the exact time is increasingly important. The telecommunication industry relies on accurate time for the transfer of vast amount of data. Utility companies use time synchronization to manage power distribution. Financial services need exact time to timestamp transactions and ensure traceable records. Satellite navigation depends on precise time with a difference of 1 microsecond causing a position error of 300 meters. Last but not least, CCTV and speed camera requires an accurate timestamp to be accessible as evidence. Countless businesses rely on precise time to manage their day-to-day processes, such as synchronizing clocking systems. For organizations of any size, NTP is a cost-effective, reliable, and user-friendly method of distributing precise time throughout a network, allowing users to boost productivity, improve customer service, enhance security, and more. Moreover, by using NTP to synchronize to UTC, a global time standard, organizations and governments are able to coordinate international operation. Now, what is UTC and how is it decided? As life becomes digitized and automated, the exact time is increasingly important. The telecommunication industry relies on accurate time for the transfer of vast amount of data. Utility companies use time synchronization to manage and power distributions. Financial services need exact time to timestamp transaction and ensure traceable record. Satellite navigation depends on precise time with a difference of 1 microsecond causing a position error of 300 meters. So we've gone over that already. So countless businesses rely on exact time to manage the day-to-day process, such as importantly, UTC is a timestamp, not a time zone, which means it's the same all over the world. It isn't affected by daylight savings. In fact, time zone are expressed accordingly to the offset from UTC plus minus number of hours. UTC is maintained by comparing more than 200 atomic clocks located all over the world. The Bureau International des Poids and Measure BIMP in France is responsible for collecting this data and generating definitive UTC time. So how does UTC work? So we're preparing a slide here with different equipment to make UTC, to set up UTC. So a time server and antenna can synchronize a network to UTC. So UTC makes NTP makes UTC available to an organization by taking a time signal from one or more atomic clock and distributed it to network devices. So it is most basic. An NTP network is comprised to the device to be synchronized, known as client, and the NTP server, which receives the UTP time and provides it to the client. Client and server communicate in a series of requests and response. So the client sends an NTP request packets to the time server, time stamping the time as it does so the original timestamp. The server stamps the time when the request packet is received. The received timestamps. The server stamps the time again when it sent a response packet back to the client and transmit timestamp. So you could read that yourself. Now let's continue. The NTP hierarchy stratum levels explains. So we get stratum 1, 2, and 3. So how devices on one stratum can provide time to devices on the next stratum. We'll see here. So stratum on server, one server have a direct connection via the radio or GPS signal with the primary time source, and they provide that time to client on stratum 2 via a network connection. So what is NTP and how is it different? Simple network time protocol. It's exactly what its name suggests. A stripped down version of NTP that's suited to small networks and computers with limited processing power. NTP and SNTP and NTP share several similarities. For example, the packets of data exchanged between the client and the time server are identical, making any time server compatible with both. However, SMTP lacks the many algorithms the NTP uses to determine and maintain synchronization practically. For instance, NTP calculates the drift rate of a given clock from one true time and adjusts the rate to maintain the clock's synchronization. SMTP, on the other hand, allows the clock to drift and then jump the time forward and or back to match the true time at given interval. So between these intervals, it's possible for the clock to be out of sync, making SMTP unsuitable for application for demands of the highest level of precision. Now, SMTP also differs in the number of servers it uses for synchronization, whereas NTP allows client on one stratum to act as server to clients on the next, as MTP is based on a single server client relationship. Now you can see here a public NTP server versus a local one. So it says this one is bad and this is good. So this is just different pictures and architecture that we prepare here for you. This is stratum 0, the GPS satellite, stratum 1, which is NTP time server, and the GPS antenna, and stratum 2, which is server, workstation, switches, router, and Ethernet clock. So I think this is enough for this lecture. Why don't we go ahead and pull up Packet Tracer and start making our configuration today. So this is the amount of NTP server installed easily alongside your existing IT hardware. Let's go ahead and pull up Packet Tracer and start making this configuration today. So we've been told that configure and verify NTP. I go to the addressing table, go to the IP address of the NTP server. This is for router 1 and router 2. And I go to subnet mask. Now in this activity, you will configure NTP on router 1 and 2 and allow the synchronization. So we know that. So first and foremost, let's go ahead and make this. So on step 1 on NTP server, let's go ahead and ping and verify. Say verify first the NTP server. So you see, let's enable it. Say authentication, we have to enable it. Okay. Now, let's try to ping the IP address of the NTP server. So ping, let's go ahead and pick up this IP address here. And let's paste it. What do we do? Space. Okay, so let's do it on the other one. And this one is really down for now. Just ping, space. Okay, so we get a successful ping. Now, on step 2, we're going to check the current NTP and the clock setting as. So say show let's do ent conf t. So let's grab this, then paste it, enter. Oh, let's put do in there. So NTP is not enabled. So if that's the case, let's check something here and see. NTP, I enable it, so I should leave it disabled for the purpose of this lab. Bang, 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 so where we are. Okay. Now, we can do this also. Says that, let's put do, and paste. So we get a time. Now let's configure. Now let's configure. Now let's configure router 1 and router 2 as the NTP client. Let's do the NTP client. So let's do NTP serve. Oh God of mercy. So NTP server 209.165.200. So just so you know that this IP address, we picked it up from there. There go this. Just copy it. Let's paste it here. If we could. Okay, paste and hit enter. Now we're gonna repeat the same process on router 2. Sorry. So on router 2, we're gonna say conf t. Enable conf t. Oh. Okay, so let's continue with the process on router 1. What if we say to show clock detail, get this. So basically, because of the type that we get on router 2, we gotta wait for it to be able to give us, to allow us to make our configuration. And then that should all be it to into this lab. So guys, okay, so conf t, and what we should do is to do NTP server and the IP address of the server, right? So if we do show clock detail, now we get what the time, sources, hardware, calendar. We say do show NTP status, show NTP status, NTP status. So now we good. So this is a pretty short lab, but it was good to have the lecture. So let's do now. Question: Are the clocks synchronized? So yes, on water 1 and 2, they have the same time as N1, which is the. So let's see. Do show NTP status. So do show NTP status. So they have the same time. So it's 4119. Let's pull this. We got the 4133 now. Let's see. So this is clock. So the times are sync. Could say show NTP association. Let's say do show NTP assoc. What do we get? The reference clock. Let's try that on router 1. So do show NTP assoc. So we pretty much get the same port 16 and 150. Let's try this. So port 16. So we good. All right, guys. So thank you so very much for following along with me. Stay tuned for another lab lecture. I'll see you in the next lab. Thank you. Bye-bye.